Hello, this video is regarding on hardenability. Okay, hardenability. This picture, what I'm showing you, it is the test conducted for hardenability. It's called Germany end quench test. Okay, most popular test for finding out the hardenability. Now, what is the difference between hardening and hardenability? I told you this is not a separate one. In the previous video, I told you this is the very much continuation of hardening only. Now, hardening is formation of martensite. I told you are introducing the hardness in the steel specimen. So that is possible by the formation of martensite. That is hardening. Now, how much of hardness or how much of martensite is formed in the specimen, to find that out is what we call as hardenability. So it's like a measure of hardness. The term hardenability is the measure of depth of martensitic hardening that is introduced to the steel by quenching. Okay, ability of the metal to be hardened by forming martensite. You are checking out how much the martensite is formed, how much it has been introduced. Ability of the metal to be hardened by forming the martensite, how much has been formed. Okay, so that is hardenability. The main difference of hardenability, again they are both different terms. Hardening is the formation of the martensitic phase, the hardness. Hardenability is how much the hardening, the martensite has formed. It's like hardenability is like you're checking out the hardness. Okay, how much hardness is formed. It's like a test, hardenability. It's not a process. Again, hardenability is not a process. It's basically a measure of hardness. Okay, you'll know it in a much clear way if you understand this Germany end quench test. Okay, so if you can see here, I'll go down later. If you can see here, Germany end quench test, it is quite popular to measure the hardenability under the certain conditions. Okay, so what is this test, how it is conducted, I'll discuss now. So here we take first a standard specimen of 25.4 mm diameter and 100 mm long, and that is heated in a furnace to the austenizing temperature for a prescribed time. Okay, what I mean to say is this is basically a tubular structure. Okay, it is having, when I'm talking that it has a diameter of 25.4 mm, obviously it's a tubular structure. And again, please concentrate on the same measurements. Okay, the material has been very much provided in the slides, so please follow the same facts and figures. Okay, don't alter there, otherwise you'll be losing marks. Okay, so a standard specimen of 25.4 mm diameter and 100 mm long is being heated in a furnace. It's heated till austenitic phase is formed. Okay, to the austenizing temperature for a prescribed period of time. For a certain period of time, you are heating it so that austenite is formed. The specimen will be quickly removed from the furnace and it will be mounted in a fixture. This that you can see, mounting fixture. So to this fixture, immediately after the specimen is heated in a furnace, it will be mounted inside this. Okay. Now what happens, and again as you can see here, this 1 inch, it is nothing but diameter in mm. I told you the standard specimen is having 25.4 mm diameter. It means to say the diameter is 1 inch, like 25.4 mm is nothing but 1 inch. Okay, that is what I mean to say. So it is the same specimen and it is 100 mm long. Now what happens? We will fix it in a mounting fixture. To that fixture we will be fixing the specimen. The lower end of the specimen, it will be quenched by a jet of water at a specific flow rate and the temperature being maintained at 24 degrees Celsius. What I mean to say is this water temperature, this water spray that is being given, okay, that will be at a temperature of 24 degrees Celsius. That water is at 24 degrees Celsius, and the jet of water that it is coming, that is through a pipe. That pipe diameter is half inch. Okay, half inch dia. 1 inch specimen, half inch diameter pipe is spraying the water which is at 24 degrees Celsius. Okay, that is what it means. So at one end we are quenching it. It's a heated specimen and we are quenching it. Now that results in different rate of cooling along the entire length of the test specimen. Natural, because here it will be immediately cooled, because this is the place where water is sprayed. So obviously not that entire specimen is cooled immediately, because I have not dipped the entire specimen inside the tank or something. Only this end I am spraying the jet, right? Water spray is given. That is what happens. Now what happens, different rate of cooling along the entire length will take place, and after the specimen has cooled down to room temperature, shallow flats of 0.4 mm deep will be ground. Okay, this line on that specimen, we will be just grinding. The grinding operation will be done, and that will be like around depth of about 0.4 mm. Through 0.4 mm it will be ground. The grinding will be done along the entire length, the length of the specimen, and Rockwell hardness measurement will be done. Hope you know what is Rockwell hardness. In the material testing lab, that test is done. I don't know if that lab were conducted for you online, I'm not sure, but Rockwell hardness is there in your syllabus, and that's one of the hardness testing experiment. Okay, so here we will be applying Rockwell hardness along the length, and hardenability curve will be plotted with hardness as a function. Okay, that is what you can see here, hardenability curve with considering hardness. That is distance from the quenched end with hardness. This is the hardenability curve, with x-axis being distance from the quenched end, and this is the hardness. How much is the hardness? HRC means Rockwell test. Rockwell hardness. HRC is Rockwell hardness. That will be found out, and the curve will be plotted. Okay. Now, what you can understand from this curve is, this curve, this is the highest point of hardness, correct? And this is the place where the water was sprayed. That means that portion was quenched immediately. Rapid cooling happened here because water was sprayed very much at that end. So that got cooled first. So that point will have the higher hardness. As you proceed along the length, over the length, and here you can see it is the least. Here it was the maximum, and these are all the intermediary. That means to say the end which was subjected to quench hardening had the higher maximum hardness, and the end which was quite away from this cooling point, it had the least hardness. Okay, so this is what we call as Jomini end quench test. It is clear from the hardenability curve that hardness will decrease with increase in the distance from the quenched end, indicating the decrease in the cooling rate. With diminishing cooling rate, more time is allowed for carbon diffusion and the formation of greater proportion of the softer perlite. That means to say there is greater proportion of the softer perlite which may be mixed with the martensite and bainite. That means here and there will be, because you're giving lot of time for cooling, right? So you will not immediately get martensite from the austenitic phase. Here definitely you will have martensite phase, but as you're giving lot of time here, okay, because the hardness is very less, it will go through the process of all the formation of that phase, perlite, bainite, and finally martensite. Okay, if you remember in the TTT diagram, there were several phases. So this is Jomini end quench test, where we are measuring the hardness hardenability. Okay, so that is about Jomini and quench test. In the exam, please follow all the facts and figures that's been mentioned in the diagram. I have been provided in the notes as well. Please follow this. You have to write all these three diagrams when you're explaining Jomini and quench test. Not just this, it makes no sense. You have to represent all these three diagrams. Okay, hope I'm clear. And in the next video, I'll be discussing on tempering heat treatment process, which is the next type of heat treatment process. Okay.